Okay, so now I have to implement a better hash. So city hash is an option. So I'll quickly go through murmur hash. So first of all, we have this operator. Okay, so this is a rotating left shift operator, right? Okay, so it left shifts it, right? If I'm not here, yeah. Okay, so bitwise left rotating, right? Okay, so our ROTL function rotate left, right? Bitwise they shift number of and the remaining positions are wrapped onto the. Okay, so first of all, okay, so going to be using mer mer 3 hash as a better default hash, right? Okay, so I just have to understand it real quick. uh Maybe I should uh, use it separately, then I'll just copy the things here, right? Okay. So this scramble won't work. I don't want to scramble. Okay. Okay, so this is murmur 32. We void key and size and length of the key, or yeah, okay. Okay, we can use that. Alright. I'll update it later. Okay, so first we have this function. Okay. So what is this? This is a simple uh, rotate left shift function which left shifts the specified bits and then appends the bits that get cut off uh, on onto the right. Right. Okay. So that is basically what this function is doing. So we take, okay, so first we will get this value, right? Okay, so I think I had notes. There we go. Okay, so I want to open paint. Okay, yeah, buddy. Great. Okay, so before that, or maybe okay, this is 4 bytes at a time. Okay, right. That is true, but I am going to needing. Okay, so this is ROTL 32, right? So what this function is doing? It computes, okay, the right shift. Okay, so it okay. So first computes right shift of 32 minus x bits, then computes uh, left shift of x bits, right? Okay. Hmm. Appends dash logical or both the values. Okay, right, so that is basically what this does. Okay, so we have this right till 32. Okay, then git block. Okay, so this is git block 32. So the second one is force inline. I think force inline is already defined. Inline attribute always inline. Oh, just go inline. Inline. I'll make it static inline. Keep it in this file. Okay, so this will help us get a 4 byte slash 32-bit chunk at a time from the buffer that is being pointed by P. That is easy to understand. Then we have this finalization mix forces all bits of a hash block to avalanche. Okay, so we'll just copy this. Okay. Okay, so says finalization mix forces all the bits of the hash to avalanche. The avalanche is a property that a difference in single bit should have at least a difference of single bit in the output should result in a difference of half the amounts of bits in the output, right? Avalanche behavior is crucial for all hash functions, which says that a single bit change in the input, should be reflected by at least half the bit changes in the output. For 32-bit hash, if one bit is different in maybe I should take it in give a 32-bit hash. If one bit is different in input, then at least 16 bits should be different in the generated output hash. Okay, we have this. Okay. So then we have murmur hash 3, murmur 3, murmur 32. Yep. Okay, so I'm writing this for ex86 copy of murmur 3 x86 32 function. Right, okay. So we have a key, we have a length, then we have a seed, and then I have a void out. Okay, so I want to return void out, I think in the, yeah, okay, h1, so I'll just return h1. Okay, alright, so we go. Right, okay, so we start with the single byte pointer pointing to the right. This should be const void okay. Hash start with a seed h1, right? Int h1. Okay. Hash start with a seed using 0 by default. Okay, then int k. Okay. You point to the data in byte fashion. So we have read only on side integer 8 pointer data, which we will be 8 t okay. In byte fashion we compute the number of now we compute the number of 4-byte blocks. So we have this constant blocks equals len divided by 4. We will handle the remaining bits at the end, right? Then we have a seed, then I'm defining 2 integers. Okay, then I have seed. Okay. Hash, so this is where signed int 32 hash starts with a seed. This will contain our computed hash at the end. Okay, so we have these constants, right? So const 32 bit inside integer 32 c1 equals, I think I should just copy this. Constants to be used later, right? Okay, then we have body, then we are with okay, so we are directly pointing to the okay, I got it. So we go, now we will point to the end blocks. Okay, so I think get block function will be used. Wait, there's no, okay, so we are operating on 4, right, vi. Okay, we will point to the end of this data, end of the data. This is n blocks. Okay, so this is n blocks, line divided by 4. This will point to the end of the data. Basically the most significant bytes, right? So we are n blocks time 4, so we will get so okay, so this is, so we are skipping in byte 4 byte fashion. Okay, so we have constant sign integer 32. This is blocks equals 32 t data plus n blocks times 4. Okay, so here we are using the data pointer to point. Okay, hold up. See, let me draw this. Let me call it B. Okay, see, you have data pointer, right, which points on single bytes, right? Say my message is hello world, so I'll be H E L L. Oh, let's say my message is hello. Right. Let's keep it simple. Okay, so data can point to 1 byte. This is 1 byte. This is 1 byte. This is 1 byte. This is 1 byte. And null character. Okay. So data can point to these directly, right? Right. Then we have the blocks, right? Then we compute n blocks, which will be 1. 6 divided by 4 equals 1, right? And then we use blocks pointer to basically point O and 0 and then 4 blank spaces in here. Okay. So this is 4 byte, okay, and we are pointing here. Points at the end, right? Basically point at the end. Okay, then we are going with until we reach. Okay, so we are starting. So we will start SP as the ex37 architecture is little endian, so the MSB is stored at the largest bit place. So we will be working our way back, right? We will be working our way back because we are pointing to the last one. Okay, so n blocks 1 into 4. So data will be pointing to, basically it will be pointing here. Okay, say if I had alright, so that is basically working our way back. Okay, so until we reach the LSB, we minus n blocks. Okay, I equals, ooh, we are taking a negative number. Negative number, negative of, okay, so basically, alright, 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 right, 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 right. Okay, so we can point, since pointers are relative, right? Okay, so it takes, this is minus, right? So it will take relative blocks. We pass block, we pass the relative, we see, so constant p and I, we are returning the value, so we will return this, right? We will be returning, okay, so bytes fashion. Yeah, okay, so we are indeed pointing towards the back because this is 0, right? And okay, hold up, hold up, hold up, hold up. I got it. I almost got it. So see, uh, since pointers are relative, we can point backwards slash negative index, right? Okay. Point to the end, right? We are pointing to the end at the top. Since pointers at the largest distance will be working, we've stored. Okay, since pointers are relative, we can point text, which would return the ls. Well, I don't know why this code is complicated for some reason, but anyways, okay. Which would return the LSB, return the 4-byte chunk pointing to LSB and moving and making what? Making a way hold up. Okay, I got confused again. Okay, so this is a 32-bit chunk. We are pointing to the MSBs first, right? To the end. Then we have a negative index, right? Okay, so we are negative index So this pointer with the negative index would get me ith 0th position, right? Okay, so blocks. So go blocks of, okay, total blocks, and minus, it points to the end, so minus of that would be in the front, right? Okay, points to the end, so minus of that should be in the front. Okay, front, but but okay, now it makes more sense, because the way these blocks are, right, say I have let me take a little big number, right, okay, blocks, okay, let's take data. Let's say data is a little longer. Okay, hello world is better. I think let's call it hello, then world. Okay, 1 2 3 4 5, 1 2 3 4 5 10. Okay, and the, okay, whatever. Okay, so this is 11. Okay, 11 is the length. So we will have n blocks. N blocks equals 2, right? So 2, and remaining bits will be 3. Okay, so if I go 0 1 2 3 4 5 6 7 8 9 10 11, right? Okay, so now let me come here. Okay. Now so we have n blocks, right? Now the blocks would be like data pointer plus n blocks into 4. So we go n blocks into 4, this into 4, this. Okay, right. So we will be pointing here, exactly here, because this is base address. We add it, we offset, if we offset by 4 bits, so we get here. Then we again offset it by 4 bits, so we get 4. Okay, 4 5 6 7 right here. Okay, so blocks is basically pointing at L, D, and this, nothing. Okay, so we have H, E, L, L, O, W. Give it a little room, dude. Okay, W, O, R, L, D, and this. Okay, blocks. Okay, so basically blocks is pointing right here, right, like, okay, so blocks is pointing right here. Then we go that we want a negative block, we want right, then in the loop, within the loop, right, we go, say pointer p is equals to blocks of negative 2. So this would mean p equals p minus 2. So this is current, this is 1, right, and this is 1, negative, and this is 2, right? So I was right, it points to the MSB again. Okay, so yeah, making our way back from there. Okay. Okay, so we point, right, then we also point to the tail again. Okay, okay, so the remaining this tail. Alright, 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 alright. Okay, so I can take this and simply we point to the tail for the remaining bits. However, some MSB will be left untouched in this fashion. Okay. Now we point to the remaining bytes through tail pointer. Which will address the individual bytes. If constant sign and tail with data plus, right, it's data plus and blocks time 4, blocks time 4, right. I have n blocks, right, which will address the individual bytes. Okay. Okay, so with tail again we are pointing at this place. Okay, then we go, got it. Okay, then we have tail, right. Okay, so I need to 4 bytes, 4 bytes, 4 bytes. Okay. Okay, so we have tail. So show blocks pointer points here, but it comes back. That is start. I think that is at the start. Okay, then you have a tail pointer. I'll point it here. Okay, it was not that complex. Okay, no, the byte manipulation says I don't want to get my hands in this whole bit manipulation stuff. That is for you. Okay, so we just okay, so if 3, obviously we want to hit all. If there is 2, we want to hit 1. If there is 1, then there we go. Okay, so this is a nice way to tell how many bits are left. Okay, we get targeting 3, so this will be 1 1. Right, we end it with, okay, so we are checking bit masks. if it is 3, that means all the 3 bits are untouched. If it is results in 2, that means 2 bits are untouched. In a decimal one, that means single bit is untouched. Okay. Or we can take the equivalent of taking the mod, right? That is the mod is 3, then we get this. Mod is this. Okay. Maybe it is the right. Okay. This is equivalent to taking the mod with. Okay, so I point, then we create temporary variable. But it equals 0. Okay, so we create a switch. I'll just copy the stuff. Huh. Do we ever need to put this on a switch? I don't think so. 12 right. I have ROTL 32. Okay, so we are basically checking how many bits are left which not be grouped in chunks of 4 bytes. So how many bytes are left which the expression in switch is equivalent. Expression in switch is equivalent to len mod 4. Okay. If if 3 remaining, we are using the following property of switch cases to handle the we ended. Okay, so if only these values. Okay, we are using the following property of switch cases to handle the to handle the remaining number of bytes. This is a positive number, so it would point forward. Okay. forward as n. Okay, case 3. So we go to the. Okay. Okay, so this means 3 bits are remaining. Okay, this is a single bit is remaining. Ah. Okay, so tail. Let me point it. Hello world. Okay, so tail points here. So it will manipulate, right? Okay. So it will basically manipulate. Okay, wait. So it doesn't take into account. I don't think it takes into account the null character, but just for the effect of it, right? Yeah, because in C++ strings, the null character is not specified when we compute the size. Yeah, so okay. So this computes here. If two are remaining, so it will first go to this, then this, then this. So this is one order of operation. Operated upon from right to left. Okay, so we do that, and then it's just finalization, right? Oh shit, so I should call it H1 since I've basically used H1 everywhere. Or yeah, okay, so we call it H1, and that is it. Then the finalization. And upon finalization, we just do this. For launch behavior, and then I return each one. Okay. So I have this function. Okay, so let me go murmur 3 hash yeah. Okay, can I hash generate with seed 0? Right, I have provided a seed. Does it use that seed? Okay, hold up. Where is the seed used? Is it even used anywhere? There we go. Okay, so takes in the seed. Okay, H1 is the seed. Okay. Right, okay, so I'm just starting with 0. Alright, okay, okay, then I give another definition of, okay, this is given within, inside, okay, right, cannot define 2 times, and okay, hash murmur 3 hash online. This is 32-bit result. Okay, so I just optional seed positive integer is 0. Okay, so hello. Right. Oh, so murmur 2. So option seed is 0 and hello. Okay, I've implemented this. Right, x86 32 bits. Yes. Okay, so it should be equal to this. So let me write a test case for that. Right. Okay, clear. Go to Sublime. Test. Okay, first of all, if there anything in test, okay, alright, so I want to create test slash say murmur underscore tests dot c. When we build the executables. Yes. Okay. Tests dot c files, and then we run those. And we run those tests. Okay, we compile and then we test. Okay. Huh. Alright. Just so first of all, I want to include. I hope sources. Yes, sources included. Okay, so I want to know unit.h. I want to include murmur3.h. Right, okay. So I have char test test hash null. Okay, so it was char hold up, I would need to bring up what is it .h file. Okay, so sweet start. Alright, so we need to set sweet and run test. Okay, mu run test. Okay, alright, so go all tests. I go mu sweet start. Is that right? mu sweet underscore start. mu sweet underscore start. Then I go this is underscore run test. Test hash. I hope I'm doing it right. Okay. Right. So I want to call 32 hash equals, this function is called murmur 3, it should be murmur 332. Murmur 3 underscore 32. Okay. So murmur 3 underscore 32 with I'll send hello. And it's 5. Assert hash should be equals to, what is this number? This number, wrong result for hash. And that is basically all. So it hits the all. Okay, so I just go make given arrow. Okay, alright. 32 is unsigned. Oh shit, blocks 51 51. My bad. Okay, then what else do we have at 54? Yeah, okay, so it basically solves that problem. 54 13, right? This is at, okay, this is 51, this is 58. 58. It blocks block, yes. Okay, maybe I should just rename it to ROTL32. This ROTL32, and at the end ROTL32. Have I defined clean in the make file? RM source slash remove all the object files and then remove tests. Huh. Failed. Okay. So we have make. Yeah. Okay, then debug.h. Have I used debug.h? Not really. Right. I will use debug.h. It's okay, it's about time, I should go to sleep. I just... Oh, is there something wrong with my makefile? Nope. So, am I... alright. This is probably bugging it. Okay. In main function, murmur dash test. random test.c. Oh, I didn't start that. My bad. My bad. I'm so I'm so bad. Okay. Run underscore. Then we run test. Then run underscore test. Run underscore test. Then go all tests. Huh, access is denied. Ah, this whole recipe access is denied. Oh, there's a gap here, right? How is there a gap? Because there's a gap here, there's a gap here. That's why I assume. Hmm. Um. Probably this should fix. Okay, great. Okay, now go make clean. Huh. Executable here. I don't think it understands. Maybe it understands del. Hey, it should understand rm. I'm using PowerShell, right? Okay, dude, I'll stick with del. And I don't think it understands invalid switch mode. Okay, yep, I remember. Weird thing, source. Oh, test anything exe. Huh? Could not find. Source test. Okay. Great. So make this. Then we make clean. Could not find dash q. Oh. Oh. This is a forward slash. This is really so confusing. So make it. Then we clean it and great. Okay, so let me try some more. Hash equals murmur 332. Hello world with exclamation mark and sizes. This 5 6. Okay. I think I should just I can just put it all in a single header file, right? But then that header file would be copied everywhere, so I would just simply just copy it and paste it in the file anyways. Okay, hello world, if this is 6, then this is another 6, so I'll say 12, right? Hello space 6. This is 5 and then this is 6. Okay. 12 and you assert hash should be, let me check, hello world, this number here. Wrong result for hash. Let's make, okay, great. Okay, say I mess it with a 2. Yeah, okay, alright. So it works. Alright, so next time I'll. Okay, I think I should focus on on one exercise or on one chapter in a given subject. That way, I will get more done instead of jumping through and on. So, like, see, I can give some days an hour or 2 hour, right? That would be much better. Okay, that's it for today.